So today we're going to talk about 8.2, the nature of covalent bonding. The octet rule in covalent bonding. In forming a covalent bond, atoms share electrons to gain their octets. So when we're talking about ionic compounds, they uh, gave or accepted, gained or lost electrons to form their octets. Here they're sharing. They're too close in electronegativity to um, have one take it from the other. Nonmetals tend to form covalent compounds with other nonmetals, or metalloids usually. A couple of minor exceptions throughout there, but uh, generally it's nonmetals with nonmetals or nonmetals with metalloids. Single covalent bond, atoms share 2 electrons. Double covalent bond, atom shares 4 electrons. Triple covalent bond, atom shares 6 electrons. And while there are a couple of compounds out there that I've heard of that have quadruple bonds, it's exceptionally rare and actually happens with transition metals, and it's nothing that we'll ever study in this class and probably won't study in college unless your professor happens to be the person who discovered this, in which case that's why I know it. Structural formula represents the atoms in a compound, with the bonds represented by 2 dots or a dash in the covalent compound. So for your single bond, you've got 2 dots or a dash. Double bond, 4 dots or 2 dashes. 6 dots or 3 dashes for a triple bond. Um, these are a little off on the oxygen and nitrogen. First of all, the nitrogen, those 2 electrons there should be together. Those two should be there. Those two should be there, and they're both missing one. So I should have paid closer attention before grabbing that picture off the interwebs. Shared pair or bonded pair of electrons are represented by 2 dots or a dash, like we saw. Unshared or unbonded pairs are just 2 dots. Every once in a while, you'll see something where they've got another line to represent the 2 dots, because sometimes chemists are a little lazy when it comes to drawing 2 dots as opposed to a dash. Coordinate covalent bonds. Both electrons came from one atom. After they're formed, there's no difference between a coordinate covalent bond and a normal covalent bond. You cannot tell which one in the compound had the coordinate covalent bond. It's just an accounting thing. We can represent them by an arrow pointing away from the atom that contributed both electrons. Normally, because there's literally no difference between them, we don't worry about that. Polyatomic ion is an ion containing more than one atom. So here's a couple of examples of coordinate covalent bonds with polyatomic ions. Water reacts with an acid to form hydronium ion, which I believe I have written on your common ion sheet. Ammonia reacts with an acid to form ammonium ion, which I know is on your common ion sheet. So bond association energy is the energy required to break a bond between 2 atoms. The higher the bond association energy, the stronger the bond, therefore the less reactive it is. So some examples. HH is 435, CC single bond is 347, CC double bond is 657. Notice it's not quite double. That's because the every multiple bond you add, they're getting a little closer together, and the nuclei repel some, so that's why it's just a little less stable than double, or triple if you look at the triple bond. Because organic compounds contain CH and CC bonds, typically they're relatively unreactive. By the way, these red parts here are one of the essays on the study guide, so you might want to keep track of that. So less energy stored in the bonds of the products, the more likely the reaction will release energy. Most reactions are exothermic, but there are a few due to other reasons why they exist that absorb energy, which is good because we get ice packs out of it and stuff like that. Resonance, multiple valid ways of writing a structural formula of a compound. So in all actuality, really exhibits a hybrid of the structures. Apparently I made the picture too big. So here, we could have the single bond on these two oxygens and the double bond over here, or we could be on these two oxygens for the single bond and these two for the double bonds. Both of these are valid ways of drawing the structural formula. Um, and in all actuality, if we do the chemistry on it, we find out that it's got bond association energy of about 1.5 bonds for each of those, and not one of them is a single and the other one's a double. And for sulfur dioxide, uh, I believe this is actually the preferred version because you see how we could have the electrons going to just this one, or we could have the electrons just going to that one. There's actually a third resonance structure, and it averages out to this one over here. Um, so exceptions to the octet rule. There are various exceptions that you might run into. If the central atom has fewer than 4 valence electrons, it usually can't form enough bonds to fill an octet. So beryllium chloride, you see beryllium has 2 valence electrons because it's group 2A, and so it'll form 2 bonds. Boron trichloride, again, boron has 3, so it's quite happy to just have the 3 bonds. Now, it can react to get a 4th one, and it would be a polyatomic ion at that point. That's very important chemistry. So BH3 is called borane, and it will readily react with an acid to form BH4 plus, which is super important in organic compounds. Nobel Prize was awarded to the professor at Purdue for discovering borane chemistry, because normally breaking a double bond into single bonds fairly easy in organic compounds. They just add a couple hydrogens or a couple things. But forming a double bond from single bonds, getting rid of some of those electrons, that's really tough. And that's where something like borane would work. Just a little side information. If the total number of electrons is odd, it's impossible to get 8 around all the atoms. And since the central atom is the least electronegative, it will be the one that takes the hit. So we've got 2 resonance formed here for NO2. And so a double bond on this side, or single, single or double. And we can see that there's actually a positive charge and a negative charge technically on them, as the 2 electrons are coordinate covalent bond. And this is actually one of the principal components of smog. One of the other key ones is N2O4, where 2 of these molecules will just bond to each other if the energy is right. I forget if it starts as N2O4 in the morning and becomes NO2 in the afternoon, or if it's vice versa. But one of them is kind of a brown gas that kind of chokes you, suffocates you, makes your chest feel tight. I think it might be the NO2. And then it burns off in the afternoon, quote unquote, burns off. And then it comes back because, well, you didn't actually get rid of the compounds, you just had a reaction take place. Central atom has 5 or more electrons and is in the 3p, 4p, 5p, 6p, or 7p orbital. Presumably 7p, although those elements last such a short period of time that you're probably not going to ever have any chemistry with that. But 3, 4, 5, and 6 totally could. It's possible to make 5 or 6 bonds, and thus the central atom will have 10 or 12 electrons. It's not very often that this happens per se, although sulfur is really special about it. Like where you could have resonance forms where it have single bonds with oxygens and stuff like that, it just kind of prefers double bonds with those and will gladly hybridize to something with more valence electrons around it because sulfur is special. Xenon and radon and krypton can form compounds with like fluorine. I'm not sure if they form compounds with anything else, but anytime you have a noble gas that reacts, it's going to have more than 8 valence electrons. So here you see 2, 4, 6, 8, 10. Here's 2, 4, 6, 8, 10, 12. 2, 4, 6, 8, 10, 12. 2, 4, 6, 8, 10, 12. And so these are some important compounds. Um, I don't remember what xenon difluoride is used for, but it's used for something. They don't just make it for no reason. Uh, well, okay, so somebody actually, how this came about, somebody noticed that xenon has roughly the same, I think it was electronegativity, or no, you'd have to form a compound first. Uh, Roughly the same ionization energy as like an oxygen. So if oxygen can react, then hypothetically xenon can react. And so they tested it out and found that yes, it does. It's just very rare. That's why back in the day they were called inert gases, and now they're called noble gases. They try not to mingle with the common folk, but sometimes they do. So, um, obviously, you've already done the vocabulary, so you don't have to worry about that. The assignment, start on it. We will add the next assignment on Monday to this, and so whatever you get done now stops you from having so much more homework on Monday.